Namaste. In the previous class, we got introduced to what stereoisomerism is, especially with respect to optical isomerism, who will show optical activity, and what that compound would be. It is optically active in nature. What makes somebody optically active? What are chiral centers? What is an asymmetric carbon? What are enantiomers? What is plane polarized light? And what is meant by dextrorotatory and levorotatory compound? All this is something that we understood in the last class. We spoke about a racemic mixture as well, which is an equimolar mixture of the plus form and the minus form, or the dextro form and the levo form. I gave you a couple of homework. One of the homeworks was I gave you a compound and asked you to carry out SN1 reaction for that and then identify the nature of the products. We'll have a look at the reaction there. So this is the compound that I gave you, carbon which was bonded to CH3, C2H5, hydrogen and halogen. Now, as soon as you look at this compound, one thing is clear. This carbon is an asymmetric carbon, or it's a chiral carbon. Because it's a chiral carbon, the starting compound is an optically active alkyl halide, or it is a chiral alkyl halide. Now, when a chiral alkyl halide is way to react with a nucleophile, which is OH minus, so this can give me OH minus. Under SN1 conditions, you get two products. Now, why do you get two products? You get two products because one is obtained because of inversion, the other one is obtained because of retention. Now, this product is because of inversion, this product is because of retention. Clear? So, the position of the nucleophile is opposite in this case of the starting compound. That is, the position of the nucleophile is the same as that of the starting compound. Hence, this is the retained product and this is the inverted product. Clear? So you can clearly understand with this structure here. Now here Br is on the right. So if OH minus, which is the nucleophile, attacks from the back side, clear, I will get this inverted product. And if OH minus attacks from the front side, I will get the retained product. Clear? Got that? Now observe these two products. Clear? I just wanted to focus on the products. If I place a mirror, what will these two become? Yes, these two will become mirror images of each other. This is a mirror image of this. This is a mirror image of this. Are these two superimposable? If I take this structure and put it on top of this structure, will they be superimposable? No, they are not. Non-superimposable. So non-superimposable mirror images are called as enantiomers. And looking at the products that are obtained here. Now we said this attack, OH minus can either attack from the back side or it can attack from the front side. The probability of this is 50-50%, which means this compound is obtained in 50% quantity. This compound is obtained in 50% quantity. So therefore, if I look at a beaker which has 100% of this, what is it composed of? Yes, it is composed of 50% of inverted product and 50% of retained product. Clear? When I take this mixture, we call this mixture as a racemic mixture. Clear? We already spoke about the definition of that. This mixture is called as a racemic mixture. Hence, in SN1, if we start with a chiral alkyl halide, you will get a racemic mixture. So remember, we introduced this here. Racemic mixture is formed if we start with a chiral alkyl halide. This was what the 8th point under SN1 mechanism. Okay, so now you understand what is meant by racemic mixture. And a racemic mixture is optically inactive, which means it will not rotate the plane of the polarized light, unlike the other two forms. The inverted form and the retained form, they will rotate the plane of the plane polarized light either to the right or to the left. Whereas when I take a mixture, there will be no rotation, which means if I take this substance, if I take this beaker and place it here, when light passes through this, what light comes out will be vibrating in the same direction as before. Clear? So there will be no rotation either to the right or to the left. Hence, a racemic mixture is optically inactive. So I want you to remember this. So this is one more way of explaining the same thing. So this is a chiral alkyl halide. It's a chiral alkyl halide because this carbon here at the center is bonded to 4 different groups. Clear? In the first step, there is removal of the halogen, clear, forming the carbocation. And we said this carbocation is planar. Because it is planar, the nucleophile can either attack from the front side or it can attack from the back side. Clear? It can attack from both the sides. And the probability of these two happening is 50-50%, giving us this and this as the product. So one will be the retained product. So this is the retained product because the position of the nucleophile is the same as the halogen, and this will be the inverted product because the position of the nucleophile is opposite to that of the halogen, and we get 50% of this. 50% of this product is a racemic product. Clear? So this is with respect to the stereochemistry of SN1 reactions. Clear? Then coming to the second reaction that we were talking about, second chemical property of haloalkanes, which is called as elimination reaction or EN reaction. Now, eliminate means what? Eliminate means to remove. So here we are talking about removal of something. Now, what are we trying to remove? We will remove hydrogen and halogen. What are we removing? Hydrogen and halogen. If both hydrogen and halogen is removed, then the name of this reaction is dehydrohalogenation. What is the name of the reaction? Dehydrohalogenation. Now we know in chemistry this De prefix stands for removal. Dehydrohalogenation means removal of hydrogen and halogen. Dehydrogenation, removal of hydrogen. Dehalogenation, removal of halogen. Dehydration, removal of water. So here it is dehydrohalogenation, removal of hydrogen and halogen. So what is the reagent used for dehydrohalogenation? It is alcoholic KOH. What is the KOH that is used? It is alcoholic KOH. Now it is very interesting because if you take aqueous KOH, then nucleophilic substitution reaction will happen like this. So what is this basically? This is OH minus. Who is giving that OH minus? KOH can give this OH minus. But this KOH is actually aqueous. What do we mean by aqueous? It is dissolved in water. So if I take aqueous KOH, it gives us OH minus, which will undergo substitution reaction. Whereas if you start with alcoholic KOH, it will carry out dehydrohalogenation, which means it will help in the removal of halogen and hydrogen. So how is it removed? Let's look at the reaction. Now the carbons here are mentioned as alpha and beta for a reason. We'll understand why. Now halogen goes out with potassium. Clear? Halogen goes out with whom? With potassium. As what? As Kx. Clear? So potassium takes away the halogen to go out as Kx. And look at how this halogen is going. Is it taking away the electrons or leaving behind the electrons? It is taking away the electrons. Because X is going out as X minus and the bond is taken away, what will happen to this carbon atom? Yes, the carbon atom will get a positive charge. Its valency is not satisfied. So what should happen? Somebody should give it electrons. Somebody should give it a bond. So what will happen is the hydrogen that is attached at the beta position, remember this, hydrogen that is attached at the beta position will be removed. And how is it removed? Look here, is it taking away the bond? No, it is removed as H plus. Bond is left over. Now where is this bond going to go? This bond is going to come in between these two carbon atoms. Clear? So these two electrons will come in between these two carbon atoms to form a bond. This H plus will be taken away by OH minus of KOH to form water. Clear? So H plus is taken away by OH minus of my reagent to go out as water, and the electrons that is left behind by hydrogen will get shifted to the position between carbon and carbon to form this double bond. So at the end of the reaction, we get an alkene. So a haloalkane is getting converted to a alkene. Now how is it getting converted? By the removal of hydrogen and halogen. Clear? Removal of hydrogen and halogen is called dehydrohalogenation. And dehydrohalogenation is carried out by a reagent alcoholic KOH. So very important that you need to remember, aqueous KOH carries out substitution. If you want to substitute OH in place of the halogen, either through SN1 or SN2, you need to use aqueous KOH. But if you use alcoholic KOH, then it is dehydrohalogenation, the reaction that will take place, removal of hydrogen and halogen, giving us an alkene. Clear? All right. Now, I want you to observe this reaction here. Now, forget about the rule. Don't look at what is written there. I want you to observe this product. This starting compound. Is this an alkyl halide? Yes, it is. Now, this alkyl halide is made to react with alcoholic KOH. Clear? Naturally, we are removing halogen. Clear? We will remove halogen. We will remove the hydrogen from which carbon? What did we study in the previous example? We removed from the beta carbon. Since hydrogen is removed from the beta position, this reaction is also called as beta elimination. Clear? I want you to remember this. Since hydrogen is removed from the beta position, this reaction is also called as beta elimination. Elimination is always happening from the beta position. Clear? All right, observe. Now, we have removed the halogen here. I need to remove the hydrogen. Clear? Now, this is the alpha carbon. The carbon which is having the halogen is alpha carbon atom. So, who is beta? So, this is beta. Do I have one more beta? Yes, this carbon is also beta. So, in this compound, I have two beta carbon atoms. Do I have beta hydrogens too? Yes, I do. I have I have beta hydrogens at two positions. Whereas, you look at this case here. In this case, there is only one beta carbon. So naturally, hydrogen could only be taken from this carbon. I did not have one more beta carbon. Whereas here, there are two beta carbons, which means hydrogen can either be taken from this carbon or it can be taken from this carbon. Clear? So let us see what will happen. If hydrogen is removed from this beta carbon, imagine if hydrogen is removed from this beta carbon, a double bond will be formed here, correct? To give us what is the product, this will be the product. Can you observe? There's a double bond that's formed here between. So let me just number it for our understanding. 1, 2, 3, 4. The double bond is formed between carbons 1 and 2. Clear? Double bond is formed between carbon 1 and 2. Hydrogen from carbon 1 is out. It was CH3 before, now it has become CH2, and there is a double bond between carbon 1 and carbon 2. This is one of the products formed. Look at what happens if I remove hydrogen from the other beta carbon. This is my beta carbon. Initially on 3 there was a hydrogen which is removed, so I don't have a hydrogen there, and of course halogen is removed from the second carbon, giving us an alkene where the double bond is between 2 and 3. This is the product that is obtained, which means what is the point that I want to drive here is whenever a compound contains more than one beta hydrogens, there is a possibility of getting more than one product. There is a possibility of getting more than one alkene. Will both of them be formed in equal quantities? No, they are not. You observe what is written in the brackets. This is 80%, this is 20%, which means clearly I know who is the major product and who is the minor product. Clear? So this compound is the major product and this compound is the minor product. Clear? Now who will decide which is major and which is minor? So remember we studied one of the rules in the last class. We got introduced to that as well. Addition of hydrogen and halogen to an alkene. When we are adding hydrogen and halogen to an alkene, we followed a rule called as Markovnikov's rule. And that was applicable only to what kind of alkenes? Yes, unsymmetrical. When an unsymmetrical molecule adds to an unsymmetrical alkene. Remember that? Some of you are still struggling to understand because you've forgotten Markovnikov's rule happily. So that was Markovnikov's rule. Even there you had the concept of major product and minor product. Clear? So even here we are having the concept of major product and minor product. So who will decide which is the major product and the minor product? It is decided by this rule, which is called as the Saytzeff rule. Now I want you to read this rule once. According to this rule, in dehydrohalogenation, the preferred product is that alkene which has greater number of alkyl groups. Alkyl groups are also called as substituents attached to the doubly bonded carbon atoms. Let me repeat once again. In dehydrohalogenation reactions, the preferred product is the alkene which has greater number of alkyl groups attached to the doubly bonded carbon atoms. This rule is called as Saytzeff's rule. Now let us understand what this rule actually means in this example. Now he is saying I need to take carbon-carbon double bond as reference. Okay, so let me take carbon-carbon double bond as reference. Clear? Even here, I will take carbon-carbon double bond as reference. I have put a box to that. Now I want you to observe who all are attached to that box. I need to look at alkyl groups that are attached to that box. Okay, let's look at the first case. There is one methyl here. There is another methyl here. There is another methyl here. So totally, how many substituents are attached? 3 substituents are attached, or 3 alkyl groups are attached, which are methyl in nature. Clear? So there are three methyl groups attached to the carbon-carbon double bond in the first product. Let's look at the second product. On this side of the box, I do not have anybody substituted. On this side, I have this big group which is substituted, which is considered as one group because it is only this carbon that is bonded to this carbon. Clear? So this entire thing will be a substituent. It is an isopropyl group. What group is it? Isopropyl group. Why is it an isopropyl group? Iso because it is branched, prop because there are three carbon atoms. So this is an isopropyl group. So when I look at the second compound, there is only one substituent which is attached to the carbon-carbon double bond. Even though that substituent is big, that does not mean you will consider it as more than one substituent. It is considered as one single substituent. Now, according to this rule, let us read the rule once again. In dehydrohalogenation reaction, the preferred product is that alkene which has greater number of alkyl groups attached to the doubly bonded carbon atoms. So he's telling us the major product out of these two alkenes will be the alkene which contains more number of substituents. So when I take this example here, there are three alkyl groups. Clear? Three methyl groups which are attached as substituents to carbon-carbon double bond. Whereas in this, I have only one. So therefore, this compound will be the major product and this compound will be the minor product. Clear? So very, very, very important rule. Saytzeff's rule. Okay. So you need to understand, focus on certain aspects of this rule. The first point says you need to look at removal at beta position only. Removal at beta position only. And it should have more than one way in which I can remove hydrogen. Or in other words, there should be more than one beta hydrogens. If there are more than one beta carbons having hydrogens, then hydrogen will be removed from each of the positions, giving us the respective product. Now, out of the two products, which product is major and which product is minor is decided by Saytzeff's rule. So, according to Saytzeff's rule, the product or the alkene which contains maximum number of substituents is called as the major product and the other product will be the minor product. Clear? Now let's see whether you have understood this. I want you to write the products for this reaction. See whether Saytzeff's rule is applicable. If Saytzeff's rule is applicable, find out which is the major product and which is the minor product. Do it right now. This is not a homework. I want you to do it right away, right now. Done? You're able to figure out which is the major product and which is the minor product. Done? Okay, I'll give you a couple of minutes. All right, so this is the reaction I wanted you to write. Now, first and foremost, let us understand whether Saytzeff's rule is applicable to this compound or not. Does this have more than one beta carbons. Let us observe. This is my alpha, this is beta, and this is also beta. So yes, there are more than one beta carbons. So naturally there'll be more than one beta hydrogens. Here, halogen will be naturally removed. Here, hydrogen can either be removed from this carbon or it can be removed from this carbon. Clear? So if I number it, 1, 2, 3, 4. So if I number these carbons, hydrogen can either be removed from the first carbon or it can be removed from the third carbon. Now, depending upon which hydrogen is removed, I get different products. So if this hydrogen is removed, where is the double bond formed? Yes, double bond is formed between carbon 1 and 2. If this hydrogen is removed, where is the double bond formed? Yes, the double bond is formed between carbon 2 and 3. Now we need to find out which of these two alkenes is the major product. So who will decide that? Yes, Saytzeff's rule will decide that. How will Saytzeff's rule decide? It will look at the number of substituents or alkyl groups that are attached to the carbon-carbon double bond. Depending upon which alkene has more substituent, you get that particular product as the major product. So are we ready to see the reaction? Yes, this is the reaction products. Now look at the products here. So we said halogen is removed from the alpha carbon. Either this hydrogen can be removed from this beta carbon or this hydrogen can be removed. Now if this hydrogen is removed, 1, 2, 3, 4. If hydrogen is removed from the third carbon, observe, if it is removed from the third carbon, I will get a double bond between 2 and 3, which is what is indicated in this product. 1, 2, 3, 4. Now, can you see the double bond is between 2 and 3? If hydrogen is removed from carbon 1, the double bond will be between 1 and 2. So 1, 2, 3, 4. So can you clearly see the double bond is between 1 and 2? Now, out of these two, which is major, which is minor, it is indicated by the Saytzeff's rule. Now, what does the Saytzeff rule state? It states that if in dehydrohalogenation, the preferred alkene will be the one which has more number of substituents. Now, how do you identify substituents? Put a box to carbon-carbon double bond. Here, let me put a box to that. Same way here, let me put a box to carbon-carbon double bond. Now, the moment I put a box, I can easily identify the number of substituents. Now, let's look at the first case. First case, I have 1, 2. So, there are 2 methyl groups attached to the box or 2 substituents. Let's look at the second case here. On this side, I do not have any substituent. On this side, I have one big substituent with this, which is ethyl. Clear? We said even though there are more carbons here in the substituent, it will still be considered as one single substituent only. So according to Saytzeff's rule, this will be the major product. Why? Because there are 2 substituents as compared to only one substituent in this product, which will be the minor product. Hence, but2-ene will be 80%, but1-ene is 20%. Clear? So this is according to Saytzeff's rule. Clear? You're able to understand? All right. Now, this is a very important slide which talks about what is the competition between nucleophilic substitution and elimination. Is there any competition? Yes, there is a competition between nucleophilic substitution and elimination. Now, why should there be a competition? Now, one of the reasons is the starting compound is the same. The reagent that is attacking is the same. It's a nucleophile, OH minus. That's what we have seen in the previous examples. So OH minus can be either used for substitution or it can be used for elimination. Now, whether the compound will undergo substitution or elimination depends upon certain factors. That is what we would like to see in this slide. Now, this is more important for your competitive, this concept, substitution versus elimination. So, alkyl halides can undergo all these SN2, SN1, E2, E1. Now, what is this E2 and E1? E2 and E1 are nothing but types of elimination. E2 and E1 are what? Types of elimination reaction, just like SN1 and SN2. Clear? So, elimination also can happen in two ways: E1 elimination, E2 elimination. So, alkyl halides can undergo any one of these with the same nucleophile, which is OH minus. If I have OH minus attacking an alkyl halide, any of these four can happen, either nucleophilic substitution or elimination. Now, who will or which reaction will be preferred is given by the next point here. OH minus is called nucleophile in substitution reaction and a base in elimination reaction. So this is something that I want you to understand. Now, the reagent remains the same, OH minus, but in the case of substitution, OH minus behaves as a nucleophile which will attack the carbon atom, whereas in the case of elimination, the same OH minus is removing hydrogen. It will help in removal of hydrogen, therefore it behaves as a base. So this is the difference between OH minus in nucleophilic substitution and OH minus in elimination. Then coming to SN2E2. Now, SN2E2 reactions are favored by high concentration of a good nucleophile or a strong base. So remember this. SN2 and E2 will be favored by high concentration of a strong base or the nucleophile. If I take a strong nucleophile or a strong base, then naturally SN2 or E2 will happen. Whereas if I have a poor nucleophile or a weak base, SN1 and E1 reactions are favored. Clear? So this is the simplest way in which to determine whether a reaction will happen through SN1, SN2 or E1, E2. Clear? So when is SN2, E2 preferred? When the nucleophile is strong. When is SN1, E1 preferred? When the nucleophile or the base is weak. Clear? So this, I told you, is more pronounced for competitive than PU, but very important for you to understand. Then coming to the third type of reactions, reactions with metals. Haloalkanes can react with metals. One of the metals that it reacts with is magnesium using this reaction. So RX is an alkyl halide. It reacts with magnesium in the presence of ether to form this compound. I want you to observe what's happened from left to right. Yes, when you observe what's happened from left to right, this Mg has come in between carbon and halogen. Mg has come in between R and X to form RMgX, which is called as a Grignard reagent. This is an important reaction. We will keep coming across this Grignard reagent in all the chapters. Clear? Somewhere or the other, we'll keep coming across this. I just want you to remember. Okay? So when an alkyl halide reacts with magnesium in the presence of ether, you get a Grignard reagent. Clear? I want you to take a homework. I want you to prepare ethyl magnesium chloride. I want you to prepare ethyl magnesium chloride. Clear? All right. Another important reaction that you need to understand is called as Wurtz reaction. Very, very, very important reaction for both PU as well as competitive. Wurtz reaction. Now, Wurtz reaction is indicated in the reaction given below. So I want you to observe what are the starting compounds. I have started with 1, 2, 2 moles of alkyl halide in the presence of what? 2 sodium atoms. Clear? I want you to observe what happens. Halogens are removed by sodium. There are how many halogens? 2 halogens together. Both the halogens are removed by the 2 sodium atoms to go out as sodium halide. To go out as what? Sodium halide. Now, who remains? Both the R groups remain. They will combine with each other to form an alkane. Clear? So 2 moles of an alkyl halide, when it reacts with sodium in the presence of dry ether, you get an alkane. This reaction is called Wurtz reaction. Very, very, very important reaction. I just wanted to observe this slide. So are you able to understand? All right, let's see if you're able to apply it. I'll give you an example. If I take CH3Cl and one more CH3Cl in the presence of sodium, naturally what will happen? Halogens are removed by whom? By sodium to go out as NaCl. So what is remaining? CH3. CH3 is remaining, giving us ethane. Clear? This is nothing but ethane. Ethane is obtained. Okay. So if I take methyl chloride, 2 moles of methyl chloride in the presence of sodium and dry ether, we get ethane. So what about this example here? So I'm taking 2 moles of what is this compound? 1, 2, 3. 3-chloropropane. So this compound is 3-chloropropane. Sorry, 2-chloropropane. So chlorine is attached to the second carbon. Clear? When I take 2 moles of 2-chloropropane and react it with sodium in the presence of dry ether, so naturally what will happen? Both the chlorines will be removed with Na as NaCl. So who will form a bond? One isopropyl group and another isopropyl group will combine to form this as the product. Clear? Now can you see the 2 isopropyl groups? This is the first group and this is the second group. They have come together. They have come together, formed a bond to form a higher alkane. Clear? Yes? Okay. If you have understood this, I want you to complete this reaction. I want you to complete this reaction. I want you to take this reaction. This will be your homework. So CH3Cl plus 2Na plus C2H5Cl in the presence of dry ether. CH3Cl plus 2Na plus C2H5Cl in the presence of dry ether. You will get 3 products. How many products? 3 products. I want you to write the structures of the 3 products. Find out how you get 3 products. Clear? So take this as homework. We'll stop here in today's class, complete this. We will continue with this homework in the next class. Clear? So until the next class, thank you. Namaste.